Okay, so in this lecture, I'm going to go over parts of Chapter 13 from the book. So this is kind of a supplementary lecture to the HVAC lecture that is already posted in this week's lesson. So again, all this content is from Chapter 13 in your book, and I'm basically going to go over some of the key images and the concepts associated with those images in the assigned reading this week. So you can see here we have a forced air furnace. This is a review from before, but I wanted to go over just to kind of reiterate some of the components here and how this all works. So the basic principle behind a forced air furnace is that it uses forces air across a hot heat exchanger, and it just blows the hot air out into the rooms. Okay, so you have to have all of these components working in conjunction in order to for it to work well. So you have your return duct, which is here. Okay, so your return, which is returns to the unit. Then this is air that comes from the space, from the rest of the house, and then it goes through a filter. Okay, so to filter out dust and other little particulates. And there are different types of filters, and that is gone over in your book. Then this air is then blown across a heat exchanger, which is just hot metal. Okay, it has this sort of shape, this sort of S-curve shape, to maximize the surface area of the hot metal. And then it blows it out the supply duct. Okay, and we'll go over some of the different distribution systems here in a little bit. But basically, you bring air in, filter it, blow it across this hot heating coil, and it just blows it out these supply ducts. This process is driven by the air handler or the blower. Okay, so usually it's going to look like this. It's going to be usually a centrifugal fan, and this both pulls the air in through the return and also pushes it out the supply. So that's what makes the air move. That's the forced air part. And of course we need to heat the air, so we have all of our heating components. So there's really two separate systems going on here. We have the air side system, that's the fresh air, I guess, or the indoor air, okay, that gets heated up and pushed out, and then it ends up recirculating back. So this is all kind of a loop. And then your other, I guess, your other system, as it were, is the whole combustion process, right? So we start with our gas supply. This is a natural gas furnace, but this could be propane or oil. Could be oil, although oil is slightly different. You have bring your fuel source in. It burns here in your burners, right? So you need oxygen in order to facilitate that reaction, as we went over in the last lecture. And so it's going to get oxygen either from directly from the outside, which isn't pictured here, or it's just going to pull oxygen in from around the furnace. So then you have your combustion, and these burners, there's a little igniter in there. Usually the new ones just have basically two little, it uses an arc. So there's two pieces of metal, and it just creates a spark, and then you spray the gas across that, and that's what ignites the gas. And that just heats up, and then the hot gas goes through here and heats up the heat exchanger. And then, of course, you don't want any of those gases in the house because there's carbon monoxide, there's carbon dioxide, there's particulates. You don't want to be breathing that in. And so this heat exchanger has to be totally disconnected in terms of airflow from the forced air part, right? So you have hot gases going through here that are then blowing out the flue. And they, if you have a crack in your heat exchanger, for example, that's dangerous, and you have to replace the heat exchanger or just replace the whole furnace. And that's the basic process here. There are some minor components like your power switch, your gas shutoff valve, the gas control valve, and some other components. But that's the basic premise. Now there are different types of heating systems. This is a lower efficiency. It's not a condensing furnace. but the basic process is going to be the same. You provide your return air, you heat it up, blow it across the heat exchanger that goes out your supply ducts. That's all driven by the air handler, and then you need some sort of fuel source. Now you can have electric resistance heat to heat up the air. That's less common. You can have oil, you can have propane, and then that's pretty much it. The air just keeps looping through the house. It kind of deposits its heat, warms up the rooms, and then it comes back a little cooler, warms it up, and sort of recirculates. Okay, so with a heat pump system, and again, this is a review. It's based on the vapor compression refrigeration cycle, which we went over previously. So feel free to review that video on the refrigeration cycle if you need a refresher on that. But remember, with the refrigeration cycle, we have our 4 basic components. We have our evaporator, we have our condenser, we have a compressor, and we have an expansion valve. And so with the heat pump, important to understand, by definition, it can heat and cool. Okay. If it's cooling only, it's called central air. And so remember, we've gone over this sort of ad nauseum, but when you evaporate, it removes heat from the building. So you may have detected a little bit of confusion in my voice there. I had to go over this. I basically pulled these images from the book. This is from page 330 in your book, and I just noticed that this image, there's actually 2 things that are wrong with the images on the left here, so that's interesting. As I was saying, when you evaporate, you pull heat from the air around it, right? So when we're in cooling mode, when a heat pump is in cooling mode, it's pulling heat from around the indoor coils, and then that fan is blowing that air across the cold coils, and then it goes back outside through the compressor. And then remember, with the condenser, it takes this compressor, pressurizes this cool, it's a gas at this point, so it pressurizes it, which heats it up, and then it gets hot enough, and then it actually dumps that heat outside into the outside air. So it condenses. It doesn't evaporate outside in cooling mode. And then the nice thing about a heat pump, again, is that you can heat and cool with the same equipment, and you just have that reversing valve, which then reverses the flow. Okay, and these coils, inside and outside, nothing changes for them. It's just static. It just stays there. But the refrigerant flow changes, and it converts the evaporator. What was the evaporator coils? You reverse the flow, and now they become condensing coils, or condenser. And so it looked more like this in the field. You'd have your outdoor unit like this, and there's coils sort of wrapped around here with little fins on these to facilitate the heat exchange. Here's your fan that gets gets the process happening. There's your compressor, and then your refrigerant lines that go in and out, and then you'd have your coils inside, usually in a basement, but it could be in an attic or wherever. And there's coils inside of this unit in here, and these coils, again, when you're in cooling mode, this is your evaporator, right? So it's evaporating the liquid, pulling heat from the air around it, from the air that's flowing through this return duct, and then it's flowing out. The cold air is blowing out, and then comes out here and dumps that heat outside. Okay. Then when it's in heating mode, everything just reverses. There's a reversing valve in here that kicks in, reverses the flow, and then this becomes your condenser coil. So they get actually warm. The coils get warm. You blow that air, that return air across, goes through the filter, and goes across the warm coils. And so that's the benefit of a heat pump system, is that you can heat and cool with the same components. You just have to add a few valves and that reversing valve. This is an image of a ductless mini split. Again, we went over this in the previous lecture. These are becoming really, really common because you can zone them off. They're the most efficient types of air conditioning equipment. heating and cooling equipment on a residential scale. So you can have multiple zones for an outdoor unit. So with these systems, you have this outdoor unit, and then you have refrigerant lines going in, and then you connect these refrigerant lines to these terminal units, and you can connect up to 4 terminal units for one outdoor unit. You may be able to do 6, but 4 is very common. So you can heat and cool individual rooms with these, and they're really, really efficient. They're much more efficient on average than these split systems. Another benefit is you don't need ductwork, so this is really great to retrofit old buildings that don't have ductwork in them. So these are something, if you're into residential HVAC, they're really, really common nowadays. And then you can have a hybrid system. This is also a split system, right? So we have outdoor unit and indoor unit, so it's a split system. This is hybrid because it has here's that V-shaped coils. Okay, so this is your cooling coils, your evaporator coils. Now, if this is your heat pump, you can do this as a heat pump as well. But let's, for sake of argument, say this is just central air plus gas heating. Okay, so now you have the full central air system with your evaporator coils inside. Again, all the components are basically the same, right? So you have your return duct, you have your filter, you have your air handler, and you have your coils, you have your supply duct. But this has that for cooling, and then it has natural gas heating. Okay, so then all of those components we went over for natural gas, the gas line, the burners, the flue, heat exchanger, all that. So this is a hybrid system. Now you can have a hybrid heat pump system as well, and there's a benefit to that. I mean, again, with the heat pump system, it's basically the same as central air with just a few more valves, so it's not much more expensive to have a heat pump system versus a central air system. And at higher outdoor air temperatures, generally speaking, your heat pump is going to be cheaper to heat the house, depending on the technology, depending on the refrigerant, depending on the age. There's all kinds of factors, but most heat pumps are going to operate pretty efficiently above 30-40 degrees if it's outside. Now, once it drops down a lot colder than that, then it may have trouble operating at an efficient level, and you can tell it to program it to automatically switch over to natural gas at specific outdoor air temperatures. So there's different ways to set up a split system. But again, these are pretty common if you have gas service in your area, because gas right now is relatively inexpensive. But at higher temperatures, if it's like 40 degrees outside, 50 degrees outside, you don't need to use the gas. You can use your heat pump, and it'll be cheaper to operate than gas. So something that I didn't go over in the previous lecture, but it is in your book, so I want to highlight this, is everything that we've gone over to this point are called air source heat pumps. So let's go back to this image real quick. So if you think about where this split system is getting its heat from and getting its heat from when you heat the building, and where is it dumping its heat when you're cooling the building, it's getting it from the outside air, right? So it's all coming from this outdoor unit. So when I'm heating the building, so think about this, I'm heating my building, it's 40 degrees outside, so the air is pretty cold for us, but this heat pump will be pretty sufficient at grabbing heat from that outdoor air. So remember, going back to heat versus temperature, everything has heat. A block of ice has heat in it. It's a little harder to get that heat out the colder it is. And so the outdoor air, this is when I'm in heating mode, I'm actually pulling heat from outside here, right? That's through the evaporator. And then I take that heat and I dump it back in here through the condenser, and I go back out. I pull heat from outside, I dump it inside, pull heat, and so on. Okay, so that's air source heat pump. I'm taking heat from the air. And then whenever I'm in cooling mode, I'm taking heat. My evaporator's inside. I'm taking heat from inside, and I'm dumping it. Where am I dumping it? Into the outside air. Okay, so it's still air source. Whereas a water source heat pump, instead of pulling heat from the air and dumping heat into the air, you're pulling heat and dumping heat into water. Or you can have also ground source. I should put an image of a ground source heat pump here, which is your geothermal heat pumps. And so with the geothermal and the water source heat pumps, what you do is you, instead of taking and dumping your heat into the air, what you have is you dump it in, your refrigerant lines run through tubes in the ground. Okay, so these pipes in the ground. So the benefit of that is if the temperature under the ground, if you go down like 5 feet, 6 feet underground, it's about 55 degrees all year. Alright, so in the middle of a really hot summer day, let's say it's 90 degrees outside, hot steamy day in Delaware, if I want to cool my building, I'm trying to dump heat into 90 degree air, right? So I'm taking it from my house and dumping it into that 90 degree air. Well, it's the hotter the air, the more difficult it is to dump heat into it, because the delta T, right, the temperature difference is not as great. So it's a lot easier to dump heat into, like, 50 degree air than it is to dump it into 90 degree air. Well, if you use your water source or your geothermal heat pump, instead of trying to dump that heat into 90 degree air, I'm dumping it into 55 degree water or 55 degree ground, right? So it's a lot easier and it operates more efficiently. So that's why we use geothermal. That's why we use water source heat pumps, because it's the temperature remains more steady throughout the year. And the opposite is true in the winter, right? So if let's say it's a really cold day in Delaware, it's, I don't know, 10 degrees outside. So if you have an air source heat pump, you're trying to pull heat from 10 degree air. Instead of doing that, what you can do is you pull heat from 55 degree groundwater or 55 degree ground. There are other forms of water source heat pump. I'll actually go over this in when I talk about the HVAC systems on the Stanton campus. So there are other ways to do this, but in terms of residential scale, this is going to be your basic water or ground source heat pump. And the basic premise is when you're cooling a building, you want to be dumping your heat into the coolest air possible, right? So it's easier and more efficient to dump heat into 55 degree ground water than it is 80 degree outside air. And then the opposite is true for heating. It's a lot, the warmer the source, the easier it is, the more efficiently it will grab heat from that. So it's easier to take heat from a 55 degree ground than it is from 10 degree, 20 degree, 30 degree air. So that's the premise of your water source heat pump for the most part. In drier climates, you can use what's called evaporative cooling, and this uses your basic the principles of latent heat exchange, like we've been talking about for months now. And so for these, you just basically take water and you sort of spray it out. There's a couple of different ways to do this, but you basically take water, have a fan like sort of pull the air across the water, and what that does is that facilitates evaporation. So just like the sweat, right? So the sweat on your skin, when that evaporates and cools your skin down, same thing. And so what it does is it cools the air, and then you provide either the cold air or the cold water to the building. So this is best in dry climates. So they use this in like the Southwest U.S., for example, where it's really dry most of the time, because you do add some humidity to the air. Now there is a way through what's called indirect evaporative cooling, which is the image over here, that you can actually pull out some of that moisture. It's a little more complex, but these are really simple. These are called swamp coolers. The ones that are direct evaporative cooling, and they operate at a pretty high level. I think the number was like 4 times as efficient as your average air conditioner. So that's a really good option in dry climates. Something we haven't really gone over in the lectures, but this is in your book, is humidity control and particulate control. So there's a couple of different ways to manage your humidity. You can, in terms of dehumidification, there's a couple of ways to do it. Now you can have a freestanding dehumidifier. These are not very efficient. They use a lot of power. They usually use on the order of 500 watts. I mean, they really are energy hogs. But what they do is they just basically pull the pull moisture from the air, and then you deposit it in a little basin. You can also use modern air conditioners, modern heat pumps will have settings where you can dehumidify the air. So remember, in order to dehumidify the air, remember what you have to do. You have to drop it below the dew point. Okay, and so if you can run there's sort of programming where you can run your air conditioner on sort of like a real low level, even if you don't really need the cooling. You can run it just enough to pull some of the humidity from the air, and then of course you have your condensate line, which you have on all of your air conditioners. So you can run your air conditioner at a really low level to pull humidity from the air as well. You can have dehumidifiers in the ductwork as well, but the most common one really are your freestanding, and then your just using your cooling system. Now, air filtration has become a bigger issue, especially in the era of COVID. The primary way that people filter air through HVAC is your freestanding filter in the air handler that goes on the return side. You can have standalone filter equipment. These are generally less effective. These use mechanical filters, which the air flows through it, and it's like a mesh. And there's different types of that, and you can look in your book for some of the different types. Whereas the freestanding usually have this electrostatic filter that sort of attracts dust and other particles. They're generally less effective. You can have filters at the room register. This is really pretty uncommon to have it in the rooms, but air filtration is really important. It keeps dust off the heat exchanger. It keeps dust off of the evaporator, which helps that operate better. It keeps dust out of the airstream, so it makes the air, pulls out some of the particulates, pulls out some of the allergens and that sort of thing. So that is an important part of it. In terms of air distribution, there are a couple of things to know. These are the 3 different types of systems, 3 fundamentally different types of systems. Okay, so we have our trunk and branch system, which is probably the most common, where you just have a supply plenum, that sort of had these main bigger ducts, okay, and then they branch off into these smaller ducts. This is what you see most often in modern houses. You can also have this is called a spider duct, and this is called radial. So the only real difference here is, see, the spider duct, you have this, again, you have supply plenum, and you have these trunk lines. So you can see this comes out to these little mixing boxes that then have these smaller ducts. Okay, that's the spider part. It kind of like spiders out. Whereas your radial is just a central supply plenum. It could be in the top, it could be in the bottom, but there's still a supply, and it just comes, these are singular ducts that go out to the spaces, whereas this sort of has these secondary ducts. That's what makes it, differentiates the spider duct system from the radial. There's a couple of things to know about air distribution. Number one, if you can help it, you want to run it through conditioned space. If you run it through conditioned space, that means, if it's a little bit, if it's not, it doesn't have to be insulated, and you just lose less heat, right? So your delta is going to be, you don't want to, like, you think about if you have your ducts running through a cold attic space and it's heating, so you have these hot air going through these ducts in this cold space, like, you're going to lose some heat through conduction. Even if they are insulated, you're still going to lose some heat. But if you run them inside, you're going to lose much less heat. They have to be insulated if they're in unconditioned space. If they're in the conditioned space, you don't have to insulate them, because it doesn't matter if you lose heat and cool. It's going to just sort of the same end result. In terms of airflow, you want to minimize your elbows and your turns, because that does compromise your airflow. For every turn, you lose some airflow, you lose some velocity. So if you have, like, especially if you have a single, right? So if you have like a single system and you have one branch of ducts that has like a whole bunch of turns, and the other one just kind of goes straight to a room, that one that goes straight to the room is going to get more air. So you're going to have an unbalanced system, unbalanced heating and cooling. Ideally, you have supply and return in every room, except for kitchens and bathrooms. You don't want to have a return in kitchens and bathrooms because of the moisture. And then, if you don't have a supply and return, you can use things like jumper ducts, which kind of jump over from room to room. You can have a door cut, which when you cut the bottom of the door. You can have vents that are in the wall or in the door that allow air to flow through. So if you don't, a lot of older houses don't have returns in every room, and so you can modify them. You can add a jumper duct, you can add a vent in the door, you can cut the bottom of the door so there's space, so it'll allow the air to flow out and to a return somewhere else in the building. But you do want to balance it as much as possible. There's different, there's a number of different types of ducts. Flex duct is fairly common. These are kind of nice because they have integrated insulation. They're not as good because they can end up kinked, and they have these little ridges, so the airflow is generally not as smooth. Whereas you have something like this, which is a compressed fiberglass, or you can have your metal ducts, of course. But you would prefer to use your metal straight duct because that's going to be the most consistent airflow. But you have to be careful, when you have elbows, you don't want to, there's different ways, different types of elbows, but you want it to be just as smooth as possible, because the more friction that you create, the less balanced your system's going to be. If you, code dictates that you have to seal all joints with mastic. You can use metal tape, but it's preferred to use this stuff called mastic. Not duct tape. Duct tape's good for everything but ducts, basically. And so you need to use mastic as the most common one. It just seals it up nicely. It has a little bit of flex in it. But you can use metal tape as well. That's just a little more difficult to do. You have to seal, when you install them, you have to seal everything. But you can retrofit using mastic as well. Some common problems with ductwork. There's a number of them. If you see these two images here, top right and bottom left, if you have leaks in one side of the duct, it can cause balancing problems. So if you have a leak, excessive leaks in your supply, what's going to happen if you have like these returns that are nice and solid and tight, it's able to really pull the air through the system. Okay. But if you have some of these supply leaks, it's sort of leaking out in this unconditioned space, now you're basically pulling more in than you are pushing out, because right on the side that's pushing out, you're losing some. So you end up with a depressurized room or building when that happens. Whereas if you have leaks on the return side, but your supply side is good, right? So you have your HVAC, your air handler here, it's blowing your air out, nice and smooth, no leaks here. Then the return, it's trying to pull that air back into this air handler, and there's some leaks coming in. What's going to happen is it's going to end up pressurizing the house a little more. And then again, going back to what we talked about weeks ago, if you pressurize the house, that's going to sort of force air out. This is going to force air to come in. So if you don't want to pressurize or depressurize rooms. Just a few other common problems. As I said, flex duct, it's okay, but if you have to hang it, right? So if I've seen this a lot, where you have flex ducts that are sort of hanging, being suspended from rafters or underneath a subfloor, and it sort of pinches it, and that's going to compromise your airflow, and that's a problem. So these are kind of a pain if you're hanging them. If they're laying flat on a like up here in a crawl space, it's a little bit better, but they can still get kinked. Stuff can get on them. people tend to put stuff in their attic and it falls on the duct, and they don't have the structural integrity that the metal ducts have. There's other things like leaks at the furnace filter. This is another really common one. Another really common one is where the registers penetrate through like a roof or a floor, and they're not tightly sealed, and you have leakage. We've talked about that a little bit, that you want to minimize your air leakage to the extent possible, so you need to have everything sealed up. So these are just some of the common problems with ductwork. Okay, so that's a review of the extra content from the book. Hopefully that helps clarify